So in class today we looked at Dijkstra's algorithm, and I'm just going to go through the run through of this once again so you can see it at home if you're interested. So what we're trying to do is we're trying to find the route from node A on this graph to node E, and it's got to be the shortest route. Now of course we could do this fairly simply as humans, but once it gets a lot more complex, so for example if I add 50 more nodes, it becomes impossible for a human to do, but it can be done in a realistic amount of time with Dijkstra's algorithm. And this is exactly how services such as Google Maps, Make Routes, or also the TfL Route Planner finds how to travel across the London Underground. So we've got this graph with these nodes, and we've got the edges here where you can travel between nodes, and on these edges is a weighting. Now this weighting could represent distance, it could represent time, it could represent cost, or a combination of those. So we start off at node A, which is where we want to travel from. That's the first thing, and we give it a label, a temporary label of 0, and then we make it permanent. We mark it to say we've visited A. The next thing we have to do is label the nodes that are adjacent to A. So from A we can get to B, and we can also get to C. So we label them with the sum total of the path length. So 0 plus the edge 4 gives us 4 here, and 0 plus 2 gives us 2 here. Next comes the most important step. We need to move to the node that has the least value, the least total value, which in this case is going to be C. So there we are. A is permanently visited with a score of 0, and C has a score of 2. And what we do is we go through all of the nodes attached to C, so that's B, D, and E, and we label them with the total path cost. So 2 plus 1 is going to be 3, so it's actually going to change this value because it's less. 2 plus 8 is 10, and 2 plus 10 is 12. There we are. So as you can see, this value has changed because we found a more efficient route. It was less than the 4 that was there. Now we're going to move again. So which one are we going to move to? We're going to move to the node with the least total cost, which is of course going to be B. There we are. Now from B, we've only got one way we can go because C has already been visited, and we've relabeled this because we got to here with 3 plus 4, and that changes therefore to 7. Whereas before it was labelled with 2 plus 8, which is 10. So again, we've found a more efficient path. We then move, because that's of course the least, and we can find that we can visit 2 more places, one of which is E and one of which is F. And the least of those is E. So 7 plus 2 is 9. We visit that, and then we know we've finished because we've got to our destination. And this is going to be the most efficient route through the network. To trace it back, what we have to do is we have to look at all the edges here and find out, if we take away the edge value from our current value, if the result is equal to the new node value. So we can tell that because 9 take away 2 is 7, this must be the shortest path. In some graphs you'll have more than one shortest path, so you'll have more than one instance of 7, for example. In this case we don't. We get to here, 7 take away 8, well that's not right. 7 take away 4, 3, that's correct. 3 take away 1 is 2, and 2 take away 2 is 0. So there we are, our shortest path found. And as I mentioned earlier, this is exactly the sort of thing that we'll be doing when we're looking at Google Maps. You can see there's a point here at each of these little corners where you could go off on a different road. There is going to be a node, and then these edges will all have a distance cost between them, and that's exactly how Google Maps works when it's trying to find the most efficient route. Of course, that also calculates things like traffic and this kind of thing, but in essence, it's just the same. I hope you found that interesting. It's called Dijkstra's algorithm. You can look it up online, and there's implementations of it in all sorts of programming languages. So if you wanted to make this in Python, you could, but at the moment we probably need to study data structures a bit more before we can create the graph in Python for it to work on. Thanks for watching.